So before we get into actually identifying mutations in a DNA sequence, I want to go over the two main types. So the two main types of mutations vary in the way that they actually affect each of the DNA sequences and what follows. So remember, if we change the DNA sequence in any way, that could potentially lead to changing the mRNA sequence, well, it will, and then it could change the amino acid sequence, which could ultimately change the protein. So the first type of mutation, and the most common, is called a point mutation. Sometimes this will also be called a substitution. When we're talking about mutations, we're going to be talking a lot about the frame of DNA. And I want you to think of the frame of a book or a sentence. Now, when we insert or delete a letter in a DNA or a nucleotide in a DNA sequence, it doesn't change the entire strand of DNA. It only changes that particular codon. And sometimes that codon can still code for the original amino acid, and that's why it can be known as a silent mutation. But there's also a kind of mutation called a frame shift. And in a frame shift mutation, this is when it actually shifts the entire DNA strand, because two things can happen. One is called insertion, and one is called deletion. In insertion, we are adding a nucleotide or nucleotides. Think about that. When you add a nucleotide, it's going to shift every single nucleotide down from that point, ultimately affecting the codons. In deletion, we're taking out a nucleotide, so that then affects all of the codons. And remember, when we're looking at amino acids using our codon chart, we have to have those 3 nucleotides in a row. So overall, those nucleotides are either going to shift down or shift up, depending on if a nucleotide is inserted or deleted. Frame shift mutations are particularly dangerous for this reason. Point mutations, there's a really good chance that it's going to be silent, or it's only going to affect one amino acid. In a frame shift mutation, it's going to affect every single amino acid from the point of the mutation on. And that's why this can be particularly dangerous. So what I would like to do is I would like to go ahead and work through some of these sequences with you and look at an original DNA strand and see how it's overall affected from that point on. So we're going to use this sheet here. And I have an original DNA sequence at the top, and this is already on the Canvas course, and you can absolutely utilize it as you would like. But what I am going to do is I'm going to actually have another original DNA sequence and go along with you. But we're going to go through this together. So we already have the original DNA sequence. The mRNA strand is written and the amino acid is written. This is how it originally was supposed to be. But somehow in replication, these mutations have occurred. And we've got 4 mutations that we're going to go through. The first thing I'd like for you to think about is we've got the codon on the mRNA strand AUG. What's the respective codon then on the DNA sequence? Well, A pairs with T, U would pair with A, and G would pair with C. So we need to find TAC. Okay, so here we go. We got TAC right here. So this AA is almost like a bumper. We're not going to really use that. Then what I'd like for you to do is go ahead and identify all of those codons from that point on. This is going to help you when you're referring back to this original DNA sequence. So we've got AUG and so on. These are the amino acids that correspond with the DNA sequence. And if we were to have this original DNA sequence, these are the amino acids that would be present. Well, what we're going to do now is we're going to look at the first mutation. And I want to start with TAC again, because we know that's going to be the AUG or the start codon. So we're going to go ahead and write down all those codons. The first thing I want you to look at is where is the difference occurring. So we've got TAC, TAC, CTG, CTG, CJGA, yep, CAT. Ooh, we've got CAT and then we've got CAG. Okay, so something's going on right here. So I like to go ahead and highlight that there. Something's going on right there. Now, let's go ahead and double check that this isn't happening anymore. Then we've got ACA. Okay, so that's not going to change. TCG. Okay, they all match on from that point forward. Notice how T replaced G. Did it affect everything after that? No. So we know right off the bat that's going to be known as a point mutation or substitution, because we are substituting that T for that G. Now, what I want to find out now, is this a silent mutation, so it's not going to change, or is it going to be a mutation that affects that protein? So what I'm going to do next, I'm going to make that mRNA strand and see if it affects the amino acid. So let's go through and make that mRNA strand. So we have A, U, G, G, A, C, G, C, U, G, U, A, U, G, U, A, G, C, U, G, C, C, G, C. I think I lost track. We got U, G, C. Okay, U, A, A. So these are all the same. So let's go ahead and add those amino acids in. Now we've got MET, we've got ASP, and these are going to take you a minute, I know, because you're going to have to use your codon chart. We've got ALA, we've got VAL, we've got CIS, we've got SER, CIS, ARG, and GLY, which is stop. All right, let's double check these. MET, ASP, ALA, ALA, VAL, VAL. That was where that mutation would have occurred. Did it change this amino acid sequence from the original? No, it's the same. That's why we're going to call this a silent mutation. Is there an impact on the protein? No, there's no impact on the protein. This is why we call this a silent mutation. All right, so the next thing we're going to do is we're going to go through this next one, and we are going to start the same part because we know TAC is going to be OG. So go ahead and draw those codons in. Okay, now let's see if we can see any differences here and there. So go ahead and take a look for a second. Any differences? It might help to have this actually just above. So this is the same as the original sequence. So TAC, CTG, we've got CGA, CAG, and CAT. Okay, so there's one. ACA, TCG, this is TAG, ACG, GCG, okay. And those are all the same, but we do have those two changes, okay. So what I want you to go ahead and go through is see if how it affects the mRNA sequence. So we're going to go through mutation number 2, and that's going to be A, U, G, G, A, C, G, C, U, G, U, A, U, G, U, A, U, C. So that's where that changes. A, U, C, because that goes with that. A, U, C, U, G, C, C, G, C, A, C, U, G, G, C, U, A, A. And that's the stop codon. All right. So obviously the mRNA sequence is going to be different from the original, okay? But I want to see, does this affect the amino acids in any way? So is it going to change any of these? We know that these are where the differences were. So let's go through and let's identify this. The amino acids. We've got MET. AUG is MET always. We've got VAL, CIS. Okay. I know I go through those very quickly. This is going to be time consuming, but I want to explain why it's important. You may be able to identify if it is a point mutation or a frameshift mutation. However, without writing out the amino acid sequence, you are not going to be able to tell me if there is an impact on the protein. Is it a silent mutation? Did it affect the entire protein? Was an amino acid deleted? Was it added? And that's why we have to go through that next step. So what I want to do is I want to go ahead and identify where the differences are now in this. So MET and MET are the same. ASP, ALA, VAL, CIS, SER. Ooh, this is different. Okay, So first of all, let's talk about what just happened. Was it a point mutation or was it a frameshift mutation? Did it affect everything after that point? No. So we call that another point mutation or a substitution because we substituted one nucleotide for another. Now, was there an impact on the protein? This one, it didn't change the amino acid sequence. This one, it did. So the impact on the protein, yes, there was an impact on the protein. This amino acid replaced SER, and also this effect ALA, okay? So there are actually two right here because we had two highlighted, okay? Do you see how we were able to identify the point mutation? So just to review again, point mutation means that it is going to substitute and it is ultimately going to either change the amino acid sequence and that will affect the protein, or it's going to actually be silent because that codon still codes for the exact same amino acid. So let's go ahead and flip to the back. And I know this is a pain that you have to flip back and forth. That's why I have this cut right here. But you guys can always come up and get another sheet from me. So first thing I like to do, let's go ahead and draw in our codon. Same thing, we look for TAC, okay? Okay, so next thing I would like to do is I would like to compare and contrast. And again, I like to have a different color to look at this, okay? So these are the same, CGA, CGA, CAG, CAG, ACA, yep, TCG, ACG, CGC, TGA, CCG, ATT. Oh, this is the original. That's funny, guys. I wrote it on the back, too. Just kidding. So, let's do it all over again. That's how you know I'm a human and not a robot. Sorry about that, guys. You do have the original sequence on the back, so you don't have to flip back and forth. Wasn't that thoughtful of me? Oh, this is interesting. We went 3, 3, 3, 3, 3, 3, 3. Ooh, there's 4 at the end. That's telling us something. Okay, let's go through this together. So these are the same. We got TAC, CTG. Actually, we don't need that right now. CAG. Ooh, okay. Huh. So we've got a cat here. Okay, ACA. So that's different. ACA, nothing's wrong with that. Nothing's different with that. ACG, got ACA. GCG, ooh. Uh-oh. This is all affected. Okay, so let's talk about this. This T replaced the G. Okay, so that one would be a point mutation. Because remember, it didn't really affect that on. But then what happened here? So let's look. ACG, okay, so, oh, do you see how we actually inserted an A there? Because from this point on, it's all shifted down. That's why this G is still at the end. Okay, so we inserted another nucleotide. So that is called frameshift. And what type of frameshift is it? Is it insertion or deletion? It would be insertion. Now, the impact on the protein. You should be able to guess this, but I'm going to go ahead and go through the mRNA sequence with you. Let's go ahead and write that mRNA sequence out. We've got AUG, GAC, GCU, GUA, UGU, AGC, UGU, CCG, CAC, UGG, CUA, AAA, UAG. Because can we use this G at the end? No. Okay. So let's write the amino acids down. We've got MET, ASP. And again, I know this is going to take you a little longer. Okay. So let's compare these two. This is the original. We've got met, as, ella, val, cis, ser, cis. Ooh. All of these are affected after this. All of them. So what's the impact on the protein? The protein is lengthened. And also, it's different from that point forward. All right, last one. And I'm going to use this now that we actually have a problem in between. The original DNA sequence is up there. So last one, we've got mutation number 4. So again, the first thing we're going to do is we are going to go ahead and draw our lines so we can identify our codons. Where do we start? We know that our mRNA codons should start with AUG, so we know it should be TAC. So let's see. AAT. Do you see a TAC? Can we even start reading this then? We don't have an AUG. Wait, let's compare. AATAC. What was supposed to go there? An A, okay? We can't even read this, so there's no start code. We can't even solve this problem. So what type of mutation is this? Well, first of all, did we substitute it? No. Did we insert something like this? No, but it was deleted in A. So what type of mutation is this? This is the frameshift, and we call this deletion. So what we do is the impact on the protein, there's no mRNA, and ultimately no protein is made. Now, last but not least, I want you guys to think about these. Identify 2 ways that a mutation can cause serious change in a protein structure. Okay? Well, let's think about the ways that were seriously changed. On the front, were these seriously changed? I mean, this one was changed, but this one was silent. Okay. These 2, though, were huge. This one we didn't even make a protein, and this one we made the completely wrong protein. So 2 ways that mutation can cause serious change is 1, it's located on a segment of DNA or RNA that contains a code for a protein. If I could spell, that'd be great. So the second way, there are actually 3 ways that I would say, but you can write any 2 of these and that's fine. It shifts each codon that follows it. And last but not least, it can alter the start or the stop codon. And that either means it's going to keep reading that protein, that mRNA strand, or it's not going to read it at all. Okay. Tony claims that mutations are all bad. Explain why he isn't correct. This is something we're going to talk about a lot when we talk about adaptations and evolution and natural selection. So a few things. It promotes diversity. It makes us different. It also increases evolution. Like sickle cell anemia in other countries is a beneficial mutation. Even though it's a detrimental mutation for us, it's a really beneficial mutation in other countries because it protects you from malaria and even HIV. And examples of this are sickle cell anemia, lactose tolerance. Most people are lactose intolerant. I am lactose intolerant. But some people have the mutation that they can actually digest milk. That's why some of us don't get sick when we drink milk, or we don't even get a tummy ache, because we have a mutation in our bodies, in our DNA strand that mutated our protein, that tells our bodies that we can actually digest that milk. If you guys have questions on this, make sure you refer to the next video.